The next several videos are going to focus on how do we interpret a mass spectrum, specifically one that's been generated using electron ionization mass spectrometry. Now remember that electron ionization used our molecule that was intact, we bombarded it with an electron, and we ended up making a radical charged species and ejecting one of its own electrons. What we're detecting here is the ion, right? And we're going to detect positively charged ions only. So we're going to ignore this electron. We will not see an electron peak in this spectrum. But what we are going to look for is our molecular ion. Now, to determine the molecular ion, this M dot plus, we're typically going to look for what the highest mass to charge ratio is going to be in the spectrum. Now, there might be lots of peaks in the spectrum, and so we're going to kind of look for what is the one that is the highest mass to charge ratio. Now, it might be tempting to do one of these small peaks, but remember, in addition to having molecular ions, we have isotopes for that molecular ion. And so one of your isotope peaks is going to be the largest of your isotopes because one of the isotopes is more likely to be in high abundance than some of the others. So when we assign the molecular ion, we're going to assign it as the kind of largest peak in the end grouping, where we recognize that this is probably our isotope that's M plus 1, and this is going to be our M plus 2. We might have something that has a plus 2 or has 2 of our plus 1 isotopes. So for instance, if you have 2 carbon-13s, you would have an M plus 2. All right, so this is called our molecular ion. So the M dot plus that I've drawn, that's our radical positively charged molecular ion. But you notice there's a variety of other things. And these are fragments, right? Because we said that this formed species has extra energy. And so while we're forming a whole lot of this, some percentage of that is going to fall apart. It's going to start breaking some of its internal bonds. And so let's consider that this M dot plus is actually, let's say it's a molecule that has, we can kind of say it has 3 components. Okay, and I'm just going to use this ABC as an example. Okay, so this is what our M dot plus actually represents. So when it's intact, we have the M dot plus. However, if we start saying, oh, this can fall apart, we have a variety of options here. Okay, so our M dot plus can fall apart in a couple of ways. We can break it up so we have perhaps breaking it here, and we can get an AB plus a C dot, okay, where the radical stays on one of them. And perhaps we're going to instead break it, you know, here. Okay. Oh, and I suppose if we broke it at this AB versus C, we could also have just the C with the charge and the AB with the dot. Okay, so that could be another option. Now, if we broke it at that purple line here between the A and the B, we could have the charge on the A and the radical on the BC, or we could have the charge on the radical on the A and the charge on the BC. There we go. Okay. Now, as this breaks up, what are we going to see in the mass spec? Okay, so we might see an AB, we might see a C plus, an A plus, and a BC. And all of these fragments are going to tell us something about the likelihood of these different fragmentation patterns in their abundance, as well as telling us something about the overall structure and arrangement. Okay, so as I look at these fragment peaks, perhaps this is BC plus, AB plus, C plus, and A plus. And what this is going to tell us is that our most common fragment is the Bc+. Okay, this means that this is probably the weakest of our fragments, of our bonds, and the A that comes off is going to be the most stable. So anytime we're looking at fragment interpretation, we're looking at what is the weakest bond and what's going to be the most stable group for our radical to end up on, as well as what's going to end up very stable with the charge. Okay. So in this case, our A+, C+, AB+, and BC+, those are all what we would consider fragment ions. Okay? Now, I want to make a clear distinction here. These are not unique individual species that were present in our solution that we put into the mass spectrometer. All of these fragments are actually representing this molecule. This molecule is the sample that went into the mass spectrometer. These fragments all stem from that sample. This does not mean that we have a mixed sample. What this means is that our molecule fell apart to show pieces that we can kind of put them back together. Okay, so that's our fragment ions. Now there's another term that we use when we start talking about a mass spectrum, and that's not the molecular ion, but the tallest ion. Sometimes these are one and the same, but in this example, the most abundant ion is not the molecular ion, but rather one of the fragment ions. Either way, we call the base peak, or we call the most intense peak, a base peak. Most intense peak, and we term this the base peak. Okay. And often you'll see the y-axis scaled to the abundance of the base peak, where the base peak will be at 100% and everything else will be relative to that intensity. All right, so these are some of the terminology we use when we identify the molecular peak. We have isotope peaks present, we have fragment peaks, and we have our base peak here. So keep that terminology in mind as you look at mass spectra and as we do some more interpretation in later videos.